Hello, John.
Hi, Xavier.
Hello again. How are you?
Can you hear me okay, yeah?
Yes, the quality of the sound is fine. It's okay.
Good.
Okay, so well, I was telling to the audience that right now I was begin. Well, I'm speaking English, so the interpreter is already translating the webinar to Spanish. And well,
Okay,
if you want, I can do a little introduction from you, and then you can begin with your presentation.
that's
So
fine,
for
so.
the Okay, perfect. So for the audience, John Dempsey is the course manager at Royal Quirrell Golf Club in Ireland, and he's graduate researcher at the University of the West of England in Bristol. John began greenkeeping in the 80s and has been superintendent of Ireland's oldest golf course, the Royal Quirrell, since 1893. Always had a keen interest in sports turf education. John has undertaken courses beginning with basic greenkeeping at the Botanic Gardens in Dublin to an honours degree in turfgrass science at Myerscough College in the UK. Currently just finished the Ph.D. in turfgrass pathology in the Centre for Research in Biosciences at the University of the West of England, Bristol, and has conducted independent research on turfgrass disease management for the past 10 years, covering extensively the subject Microdochium nivalis infection of turfgrass responses to infection, and the effect of phosphite treatments on disease suppression. Turfgrass growth and quality. John has presented his findings at numerous conferences and seminars in Ireland, Scotland, France, Germany, Norway, USA, and more recently at the Turf Managers Conference at BTME in Harrogate last January. And then this is the last one here in Campus del Césped. So for me, that's all. I just want to tell to the attendees that anyone who wants to ask anything about the presentation, John will attend your question immediately. So we are not going to wait to the end of your presentation, because his presentation has different sections. So it's interesting that you do your questions in order that you want to. Okay, so that's all. John,
Thank
you
you,
have to
Xavier.
share your screen.
All right. Uh,
Let me check. Sorry. Boom, boom, boom. Now you will be able.
Now, is that okay?
Okay. Okay, perfect.
Screen is up, yes?
Yes.
I'll begin, so if that's okay. So, thanks very much, Xavier. I'm delighted to get the opportunity to speak to our Spanish greenkeepers around the world. And I'll be talking about the use of phosphate in turfgrass, in cool season turfgrasses mostly. So today, hold on to see, is this moving on for me? Yeah. So today, today's talk will be mostly based on my last few years of research over that almost 10 years, in fact. And I'll be looking at phosphate, what exactly it is, some of its history, and current usage in turfgrass. A major part of the talk will be looking at phosphate, does it suppress Microdochium nivalis, and if it does, by what means does this suppression occur? As part of that, we'll be looking at how Microdochium actually infects turf grasses and how the turf grasses respond with a couple of compounds, and we'll see whether phosphate actually enhances these responses. So hopefully you'll find it of interest, and I say we only have an hour, so I'll keep moving on with it. I'll just give a quick background. As Xavier was saying, I've been a greenkeeper since the 1980s. I actually haven't been a manager since 1893, but actually 1993. I'm not that old. But I've been a greenkeeper since the 1980s, and it's a family business really. My wife's father was a greenkeeper before me, going back to the 1960s. And our son is actually a golf course superintendent also. So basically what I'm saying is any research I've been doing over the last few years is very much founded on, as you could say, turfgrass roots, and it all relates directly to the golf course. Academically, I did my primary degree at Myerscough College in the UK, and during the final year we carry out a research project, and my project obviously was on the effects of phosphate on the growth and disease susceptibility of Agrostis stolonifera. Very interesting. I really enjoyed doing that project, and it was quite successful. Myself and my tutor there, Dr. Andy Owen, were invited then to present the findings at the ETS conference, the European Turfgrass Society's conference in France in 2010. So again, I thoroughly enjoyed doing that, and that really spurred me on then to carry out further research. So I put together a project and approached some universities in the UK and in Ireland, and I started a PhD based on research at the University of the West of England in Bristol. And very basically the question we had to answer was, does phosphate reduce Microdopium nivale infection? And to find out if it did, what were the means of suppression? We also looked at the effects on growth and turf quality from phosphate applications. So they were the questions that we started out with about 6 years ago for the PhD, and it forms the basis really of today's talk. So what exactly is phosphate? Well, it hasn't been used in Ireland or the UK until about 2004. It was used for many years in the United States and possibly in warmer parts of maybe in Spain. I'm not really sure about Spain, but it was used to reduce disease of such as Pythium and Phytophthora. But what it is actually a form of phosphorus, and every greenkeeper is familiar with phosphorus. It's a major plant nutrient. However, it's taken up in all plants in the form of phosphate. Now, phosphate, as you can see, I think my marker might work here. Phosphate taken up in plants is basically phosphorus with 4 oxygen molecules. Phosphite is very similar to phosphate, except it has 1 less molecule of oxygen. And basically what this means is that while it's taken into the plant and translocates through it rapidly, it locks onto the various enzymes which form the part of plant metabolism, but it can't be used as a form of phosphorus by the plant. So as a source of phosphorus nutrition, phosphate is not very effective, although we'll be looking at some areas in regard to that later on. So as it can't be used as a form of phosphorus, it is very effective as a plant pathogen reducer, in fact, and it has been used for many years. As I say, it's derived from phosphorus acid, which is a pH of 2.2. So this has to be modified first before it can be used on plants, otherwise it will scorch them. Now, the original use of phosphorus acid and phosphate was by modifying it with aluminum, which formed a phosphatal, which was marketed in the 1980s in the United States and parts of other parts of the world also. But today, phosphorus acid is mostly modified by using, combining it with potassium hydroxide, and this forms potassium phosphate. And this is the most common form of phosphate used now in turf grasses. Now, there are other forms you can use. You can use ammonium phosphate or magnesium phosphate, but like I said, potassium phosphate is the primary form of phosphorus or phosphate being used. So, as I said, it's not effective as a plant nutrient, but very effective at reducing some plant pathogens. And there's quite a bit of research over the years looking at its reduction of pathogens such as Pythium and Phytophthora in other plant systems. Now you might think if it's effective against those, you think it would be effective against other pathogens such as microdocium or anthracnose. But Pythium and Phytophthora are actually not fungi. They're actually what's called omycetes, which are different organisms completely. So you couldn't say that phosphite would be effective against fungal pathogens without proper research being carried out. Now there has been some research looking at phosphite reducing anthracnose in turf grasses, and there has been some research looking at its effect on Microdocium majus, which is very closely related to Microdocium nivale, but that was in cereal grasses such as wheat and barley. Before we started our research, there was no published data at all looking at phosphite and its reduction of Microdocium nivale in turf grasses. So that was an ideal situation for us to get in there before anyone else could. This is just a piece of research taken from 2007 showing how phosphite actually can reduce Pythium in turf grasses. And what you can see here with the red marker is the levels of Pythium and the control plots that were being tested. And you can see these areas here, the use of phosphite in both times actually reduce the levels of Pythium in turf grasses. This one here actually is from Rutgers University in the United States. Again, looking at this is the level of anthracnose on annual bluegrass putting greens. This is the level here of disease on the untreated control plots. And you can see here and here the use of phosphite again reduces it fairly significantly. These are just various fungicides which of course would have great effect on reducing the disease. The next one here is a laboratory study looking at the effects of phosphite on Microdocium majus. This was done on agar plates, and again, this is the growth of the fungus, but it's Microdocium majus and some Fusarium species. This is the growth of the fungi in untreated plates, and you can see where here the incorporation of phosphite actually fully inhibited this growth, so it had a direct effect on these fungi. So my research at Bristol, starting from 2010, was the basic question was: does phosphite suppress Microdocium nivale in turf grasses, and what were the means of reduction? So there was 2 points of interest in our research. One was Microdocium and the other was phosphite. Now, normally I'm speaking to greenkeepers in the UK and Ireland and parts of Canada and the United States, and Fusarium patch, as it's called, or pink snow mold, which is caused by Microdocium, is the most common disease. Here in Ireland, we have infection from Microdocium from the end of September right through to March. It's very severe right through. Same in most parts of Northern Europe. Probably Northern Spain now you would have more effect from it, not so much I suppose in southern parts of Spain. But as you can see, it's a very dangerous and fast-moving pathogen in cool season grasses. And as a matter of fact, it actually affects 100% of golf courses in the UK every year. So at some stage during the year, you'll have some sort of Microdocium infection. It's very expensive to control. A lot of fungicides are being used. The problem is, of course, that they're expensive. They also inhibit beneficial organisms in the soil. And of course, there's in Europe, certainly, there's legislation ongoing to reduce the availability of fungicides. So these are a couple of reasons to look at alternative methods of disease reduction. And this is what we did, of course. We looked at the use of phosphite to reduce this disease. So like I said, we did our research by using a whole range of field trials and laboratory procedures. And we began our field trials in 2010. We ran them for 4 years at the Royal Curragh Golf Club in Ireland, where I am superintendent. Not since 1893, I might add. But so we had 4 years of field trials, and we had 3 turfgrass species we looked at. This was Agrostis canina, which is velvet bent, creeping bentgrass, so Agrostis stolonifera, and Poa annua, which I'm sure you're all familiar with also. We had a range of treatments which were applied from September right through to March each year, various rates and timings of phosphate along with biostimulants and fungicides. And we assessed the effect of these treatments on disease incidence on our plots. And also we looked at the effects on turfgrass quality each year also, as we looked at basically rated the disease was rated on a scale of 1 to 100, a percentage scale, and the turf quality was rated on a scale of 1 to 10. So to move on with this, in the first year, we only had 2 species available in the first year, the velvet bent and Poa annua. But basically what we found was that these here are the control plots here. The phosphate I was using contained 3,7,18 of NP and K fertilizer. So we had an untreated control here, and we had a fertilizer control without the phosphate here in the blue. And this was the mean level of disease in the first year in these control plots in both species here. And what we found was the incorporation of phosphate reduced the disease levels by about 50% compared to controls. So basically what we're saying is the use of phosphate without any fungicides was able to reduce the disease. These here were the fungicide controls, and the combination of the fungicide and the phosphate was very effective, totally reduced the disease in almost both species. This was the second year where we had 3 turfgrass species. We incorporated the creeping bent here. Again, it was the same story. The control levels are here of disease, both in the 3 species. Again, phosphate in the program reduced disease levels by about 50%. I'll just move on to this is the mean levels of disease over 4 years. So you get a much better picture here of the 3. We have the 3 turfgrass species. Again, high levels of disease over mean values over the 4 years. Again, phosphate, talking about a 50% reduction. Obviously not enough to satisfy turfgrass managers, but certainly by using this phosphate, it reduced the need and the time in applications of various fungicides. You can see here the combination of fungicide and phosphate totally eliminated disease on 2 of the species. Not so much on the velvet bent, but very effective on creeping bent and Poa annua. The effect on turfgrass quality was also very impressive. We found that the incorporation of the phosphate product enhanced any plots that received the phosphate had much better colour, density and uniformity than the untreated plots. Again, I just go to the average over the 4 years. So we found that over the 4 seasons, the quality was much better. We weren't really sure why this was occurring, but there's a number of theories, all right. But certainly, we had a great effectiveness there also. To show a few photos now of an overview of the trial plots. You can see here some of the treated ones standing out. That was in 2012. That's just a closer view of the treated and untreated velvet bent plots. These are the Poa annua plots from 2011. Again, a clear distinction between treated and untreated there. That's the Poa annua there, treated as at the height of the disease pressure. And the untreated one here is fairly well devastated by infection. Again, a creeping bent plot here, phosphite treated, and the untreated one. I'll just skip on, almost the same really. Again, you can see the clear distinction there between them, side-by-side view there. Now, I mentioned the earlier study I did at Myerscough College back in 2007, 2008, and that was a greenhouse study. We had turfgrass growing in pots in the greenhouse. This is a typical value or a picture of the phosphite-treated plots, and these next pots are in the same greenhouse but untreated, and you can see a vast difference there between the treated and untreated. Bearing in mind the greenhouse environment was ideal for the infection process. It was mild and humid, so quite a difference there between the treated and untreated. Now, I'm just going to show you now a more recent study, which helps to enhance my own particular research. This is from Clint Mattox, who's over in Oregon State in the United States. Oregon has a fairly similar climate to ourselves in Northwest Europe. It's mild and has the temperate weather coming in from the Pacific there. So he was looking at alternative methods to reduce mycodochium also. And this is an interesting slide he has. These are the control plots showing levels of disease. And you can see this one. These here are the phosphite plots. Again, a big reduction just from carrying out phosphite treatment. Interesting on this slide is he was looking at rolling and non-rolling of plots. You can see that the rolling actually reduced disease significantly compared to non-rolling. Now, he did say, it doesn't show it in this slide, but he did say that continuous rolling actually helped to thin out the sward a little bit. So you're reducing disease, but having an adverse effect on the quality of the turf. He also looked at sulfur applications, and you can see that the incorporation of sulfur also reduced disease. But the interesting part for me was the use of phosphite, which enhanced my research also. So, as I say, we did 4 years of trials, and what we summarized from that was that sequential applications of phosphate, certainly during disease pressure, will significantly reduce the incidence of mycodochium. And the combinations of phosphite and turfgrass fungicides, the phosphite will actually enhance the fungicide's efficacy. And they also found, of course, that phosphite as part of a nutrient program will improve the turfgrass quality. So these were very interesting results for us. And as a greenkeeper, growing trial plots and applying treatments was easy enough. The next part we had to try to figure out was how was this suppression occurring? Sorry. So using phosphite, there could be basically two means of suppression. It could be direct. In other words, the phosphite is acting as a fungicide and is killing or certainly stopping the growth of the pathogen. Or it could be indirect, in that phosphite is actually enhancing turfgrass defense responses. Now, all plants, when under stress, either from abiotic stresses such as drought or cold, or biotic ones such as pathogen challenge, will respond in a very complex and timely manner. They produce a range of various compounds which will help to fight off the pathogens, for example. And we looked at a couple of those areas to see did phosphite actually enhance these, which I'll be showing you later. But the direct means, we wanted to see whether phosphite actually had a direct effect on the mycodochium fungus. And what we did was we collected our samples from various infected golf greens around the country and grew them on. We also got samples from the STRI in the UK. So we took infected samples and, sorry, that's the wrong slide. We took infected samples and we plated them on PDA, which is potato dextrose agar, and you can see where the fungus was growing out of the infected leaves. So we collected that, and we had the fungus, and we grew it on various plates, which were amended with different compounds, different concentrations of phosphate and phosphate and other compounds also. We wanted to see whether different concentrations of these compounds actually reduce the growth or kill the fungus. And what we found in a nutshell basically was, sorry, my mouse is stuck here. Oh, that's grand. What we found was, this is a basic slide here. What we're seeing here is this bottom red line here is the effect phosphate, PO4, in the media, the effect it had on the growth of the fungus. And it had no effect on it. The fungus actually grew as per normal, as per the as the control plate. But what we found with the phosphate in the media was that at rates of even 20 to 30 micrograms of phosphate per milliliter, it inhibited the growth of the fungus on the plates. And at 100 micrograms per milliliter of PO3 or phosphate, growth had stopped completely after even after 4 to 5 days. And to give you a better view of that is these here. These are the control and the PO4 treated plates after 4 days. So what we had done was we had the plates which were amended with the various compounds, and we put in as a piece here a piece of infected mycelium or PDA, and we grew them on, and you can see after 4 days how much the fungus had grown. Whereas in the PO3 phosphate treated amended plates, there was no growth after 4 days. So the phosphate was actually slowing down or stopping the fungal growth completely. This is a closer view of the fungi in the plates. This is the hyphae. These top ones up here are the hyphae growing in the control plates, unamended. That's the normal growth of the fungus there. Now if you look down here on these bottom ones, you can see in lower rates of phosphate the effect it's having on the strands of the hyphal mycelium here. It's causing this convolution of the morphology, you could say. So this is causing disruption to the growth of the microdochium and stressing it out also. Again, this is another closer view of the same thing. You can see the direct effect it's having on the fungal mycelium. It's actually what's happening is it's interfering with the uptake. The fungus actually needs phosphate or phosphorus to grow like any living organism, and the presence of phosphate is actually interfering with the uptake of phosphate and interfering with the metabolism of the phosphate in the fungus. So it's causing this slowdown in growth and also causing the fungus to be stressed. These here are the reproductive spores of the microdochium, the conidia, and we looked at the effect phosphate had on these. Now these are produced in very vast numbers, and they are a means of it to spread and disperse. And what we found was, again, that in the presence of phosphate, the percent germination of these conidia was reduced. So phosphate, as with other fungal or oomycete research, phosphate was actually having a direct effect on the dispersal of the fungi as well. So again, I say we've seen in the field trials that the phosphate had a direct effect on the disease incidence, and in these in vitro studies what we found was that phosphate actually inhibits the mycelial growth and conidial germination of microdochium and disrupts the hyphal morphology. This would be causing it to release stress metabolites, and these stress elicitors, you could say, were being picked up by the plant. So once phosphate is in the plant, it actually will slow the growth of the pathogen, and the stress elicitors being released by the plant, by the fungus, will be picked up by the plant. So it's allowing the plant to respond quicker to infection compared to the untreated plant. Obviously, that would mean that phosphate actually has to be inside the plant. And I asked the producers of various phosphate products during our studies, how fast is phosphate taken into the plant when it's applied? And none of them knew the answer. They just said, well, we presume it's taken in the same way as other nutrients. So obviously I couldn't say that in my thesis. I had to say for definite how phosphate was taken into the plant. So that was the next part of our study. We had to look at when you apply phosphate to the turfgrass, how is it taken in through the leaf? How fast? Where does it accumulate? Does it move through the plant? And what happens to it? So again, to cut the story short, what we did was we used a range of turf grasses which were grown in the greenhouse. We applied phosphate to them, and we measured the take-up. Now, we had to be able to differentiate between phosphate PO3 and phosphate PO4 in the tissues. So normal tissue analysis wouldn't do that. So we had to use a process called HPIC, which is high performance ion chromatography, which separated these various anions in the plant. So using that process, we found that here in the two turfgrass species, we looked at creeping bent and Poa annua. So we applied the phosphate here at 0 hours, and we found that after 48 hours, there was a maximum accumulation of phosphate in the leaf tissues. It was taken in fairly rapidly here, as you can see. Even after 12 hours, it was up to over 3,000 ppm. But 48 hours, it was maximized in both turf grasses. So it was taken in rapidly. And then over a period of 6 weeks, this study here was done in the winter during February in 2011. So turf grass was growing slowly enough in the greenhouse. But you can see it accumulated at 48 hours and then gradually was taken away, mostly from the leaf clippings, in fact. The second part of this area here, this is the root accumulations here, which again are of interest because it shows that phosphate, when applied to the leaf, actually translocates right through the plant, and within 6 hours, in fact, you could find traces of it within the roots. Again, that's an interesting point. In both species, it was the same. Again, it's just tapered out over shortly over 6 weeks. That was in the winter, like I was saying, when turfgrass growth was slow. So we said we'd better have a look at when turf grasses were growing more rapidly, and this was done in July 2011. Again, the same thing. Phosphate was applied here at 0 hours. Again, a rapid accumulation up to over 5,000 ppms in both species. But we found a more rapid loss. And this was due to the grasses were growing quicker and leaf tissues were being removed. An interesting...
John,
yeah.
sorry.
Yeah, go.
We have a question for you.
Oh, okay.
Okay, from Carlos Venegas. He asks, how often do you have to apply phosphate for a good program control? And a second question from him as well. What about resistance of the pathogens against phosphate?
How often you have to apply it? Is that what you said?
Yes. How often do you have to apply phosphate for a good program control?
Right. Well, this slide that's up at the moment will give you a good idea. If you can maintain a level of phosphate in your leaf around, say, 3,000 ppm, which is here. So what you can see here is that if you're applying every 2 to 3 weeks, if you at this, for example, here, if you apply it again here after about 3 weeks, your phosphate levels would be back up again. So every 3 to 4 weeks should be sufficient through the winter. I'll just go back to the obviously the main time for disease microdochium is through the winter. So as you can see here, hopefully, is after 3 weeks it has gone down to about 3,000 ppm. So if you went with your next application within 48 hours, it would be back up to here. So every 3 to 4 weeks should be sufficient to help to control microdochium. Now, what was the second part of the question?
Yes, the second was what about resistance of the pathogens against phosphite?
No, not only me now, but other people working with phosphates in other plant systems haven't found any resistance, and this is because it's not acting really as a fungicide, but it's acting more, it's disrupting the use of phosphorus in the fungus. And that's the main reason it seems to be there's no resistance showing up anywhere yet. Now, there's a lot of research gone on with other plant systems, such as avocados right up to zucchinis, horticultural systems. And none of those people have found any resistance yet, so luckily enough.
Okay. Thank you. That's all by the moment.
That's grand, thanks. Now with the HPIC results, a lot of people selling phosphate are saying, that apply phosphate and it's a form of phosphorus nutrition that it will convert in the plant. But this doesn't happen. Phosphate doesn't convert to phosphate in the plant. It can be converted in the soil by various organisms, but when you apply it to a plant, it remains in the leaf or in the leaf tissues or in the roots. As this is what we looked at here, in fact, was the levels of phosphate in those treated plants over both periods that we looked at. And as you can see, the phosphate was applied here, and there was no increase or change in the levels of phosphate. So this reinforced the argument that phosphate does not convert to phosphate. So that's an important looking chart also. So like I was saying earlier on, I'm just looking for a slide here, the phosphate is going to inhibit the disease either directly, like we've just seen in the in vitro studies, or indirectly by enhancing plant defenses. And plant defenses are quite complicated. We've seen the in vitro work as phosphate has a direct effect on the plant. But when a plant is being, sorry, my mouse is stuck here. Right, when the plant is being infected by any sort of pathogen, it responds in a number of ways. It can be quite complex. One of the more rapid responses is induction of various compounds, such as phenolic compounds, which form antimicrobial, have antimicrobial effects, such as phytoalexins. A second area of interest is hydrogen peroxide, again, which has a direct effect on the invading pathogen, but also acts as a signaling compound, which triggers various induced or systemic resistance within the plants. So we decided we'd have a look at two areas. I didn't have time or the money to get very involved in this, so we looked at total phenolic compounds within the plant and hydrogen peroxide as a means of defense. So to do that, we first had to look at how microdochium infects the plant, the turfgrass, and how these infected turf grasses responded. So then we could see whether phosphate had any effect on these responses. So the infection process was interesting. Again, we used some greenhouse plants and some infected trial plots and golf greens. So we collected the various tissues and we used a number of techniques using light, and we used fluorescence microscopy, which means we were staining the tissues with stains which actually adhered and responded to the fungal cell walls. And when you view them under ultraviolet light using the microscope, they fluoresce, and it makes it very easy to see where the fungi or the hyphae is and how exactly it's entering the plant. We also looked at used other stains which actually fluoresced with these compounds we wanted to look at, the phenolics and the hydrogen peroxide. So you can see as we go through this very clearly what's actually happening in the infected plant. So what we found from our studies was this top picture here is a golf green root zone, which had years of infection history behind it. And we found most of the golf greens that we looked at, we took samples from these upper areas here, and we used our stains and microscopes, and we found this, for example. You can see these fungal strains right through the soils. And these fungal hyphae were there right through the year. And when the environmental conditions were right, they would start growing and start infecting the plant. And we found any areas that we looked at, it would start at the interface of the plant and the root zone, and the hyphae would grow up through the plant into the crowns and then enter the leaf through any areas we saw the fungi entered the plants through the stomata, which are the respiratory openings on the leaf. This has been seen by other researchers also, such as Tom Styang and De Joule in Guelph University in Canada. They looked at the same sort of infection. They found the fungus enters the plants through the hyphae. What happens then is it actually is that they're entering the plant. You can see it goes through the plant, through the vascular system, and the fungus then extracts nutrients for itself, obviously, and then exits the plant again through the stomata and produces a vast amount of the reproductive structures, the conidia. So that was the process of infection. Obviously, we wanted to see how the infected plants responded, and I'll just show you a few photos first of some of the infection tissues. You can see here, this is a creeping bent leaf here with the massive hyphae growing on it. And again, there's another one here. You can see the amount of fungal growth here. And actually, you can just barely make out where it's entering the into the stomata there. This here is a closer view again. Again, we use a couple of stains here. This is the infection hyphae. And where it's entering the plant, there's a fluorescence here of phenolic compounds, which are antimicrobial compounds being produced. Same here on the bottom photo. You can just barely make out where it's entering the plant. This one here is showing actually the production of conidia from Sporodokia as it comes out of it's coming out from the infected plant, and it's producing this mass of reproductive structures, which are then spread either by water, by rain, or they can actually be, of course, spread by machinery also. So these get back into the soil area, and again, when conditions are correct, they start growing and start producing more infection hyphae. This is just another few photos, again showing some of these here are the infected stomata. The red is actually autofluorescence, it's called, of the chlorophyll. So when viewed under ultraviolet, the chlorophyll actually fluoresces a reddish color. Again, this one here is the infection hyphae, and you can see clearly where it's entering here, and this bloom of phenolic antimicrobial compounds being produced, and some hydrogen peroxide actually as well. Again, same down here. This here on the right hand side again is an infection area, but the blue here is a stain. It's showing generation of hydrogen peroxide as a defense response. So we wanted to look at two areas of defense compounds, and the first one we looked at were phenolic compounds. Now, phenolics cover a wide range of compounds, which you could look at individually if you had the equipment and the time and the money. But we looked at just the total amount of compounds being produced. Again, they're important for defense response, not only for pathogen attack, but also for cold response. And cold acclimation is very similar to defense response. So you will find, of course, that plants have been acclimatized to cold will actually respond better to infection than unacclimatized one. But we need to sort out first whether or not phenolics were part of the defense process. And what we did was we looked at infected and uninfected plants over 3 years. We looked at them in the greenhouse and in trial plots outside. And these here are from the greenhouses. And you can see it's from 2012 to 2014. And it's showing the total amount of phenolics in the tissues. And you can see the control, the uninfected plants were low enough. The infected areas were all significantly greater in both turfgrass species we're looking at. So this shows, in fact, that yes, phenolic compounds are being produced as a response to infection. So that was the first step we looked at. So next thing we wanted to look at was, does phosphite actually promote the production of total phenolic compounds? And again, this was taken over following 6 months of sequential applications of phosphite. These are the control levels here. We use phosphate as a sort of positive control to see had that any effect. And yes, phosphate itself actually increased the levels of phenolics, but the phosphite was significantly better than phosphate and much better and much higher levels of phenolics compared to the controls. So that study there showed us that, okay, phenolic compounds are a form of defense against pathogens, and pre-treatment with phosphite actually was enhancing these responses even prior to infection. This one here is a little bit more complex looking. A lot more complex looking than this one, I can tell you, but this was from the greenhouse as well. And what we did was we used our turf grasses, and some of them we applied phosphite for 6 months prior to infection, and some received one application, as you can see. So one application of phosphite, some of them had 6 over the 6 months, and some of them had phosphate applied, and others had no phosphate or phosphite applied. And this here, what we did then, of course, was we inoculated these plants with microdochium. So we infected them manually with microdochium. At 0 days post-inoculation, you can see the levels of phenolics in both species were much the same, except for the phosphite-treated plants, which already had higher levels. And as you go over the inoculation period from 0 up to 10 days, you can see that the phosphite-treated plants, the levels of phenolics were in fact greater each time than the phosphate or the controls in both species. So again, as a defense response, phosphite was enhancing this area. This is just a photo of another infection looking at the light yellowy color here is actually phenolic compounds being produced at the area of infection. Again, that's the hyphal infection area there entering the plant, and this burst of antimicrobial phenolics being produced. Same on this one here. So, as I said, the second area we looked at was hydrogen peroxide. Again, a very important compound for direct response to pathogens, and also for signaling throughout the plant to enhance systemic acquired resistance for later infections as well. Again, we looked at, we extracted the hydrogen peroxide from the plant, but we also used staining processes as well to see, to visualize where the peroxide was being produced. Again, this is what we found. When we extracted the you can see the infection here, and this is actually hydrogen peroxide now being produced, not phenolics. Again, this is another infected stoma here. Again with a burst of hydrogen peroxide, and much the same on these ones. Now our study with hydrogen peroxide wasn't as successful as phenolics. It was much harder to get a distinct or significant effect from phosphite. But our infection studies, what we found was that in the field and in the greenhouses that we looked at, that Microdocium hyphae are the main source of inoculum. In other words, it's the hyphae which infects the plant, and the conidia then are used to spread the disease. Not exclusively, but this is the main source of spread. We found that the phenolic compounds, yes, are in fact a main response to infection, and that phosphite actually enhanced these. The study into hydrogen peroxide wasn't as successful, but looking at the visualizations using the staining, there was a more rapid production of hydrogen peroxide compared to the untreated ones. So we can see that yes, phosphite does enhance or does promote indirect responses to infection. So we've seen, like I said, that phosphite, the main study was into its reduction of disease. But as a turfgrass manager, I'd like to know, when you're applying a compound or any sort of product to my turfgrass greens, what other effects would it have apart from stopping disease? So we decided we'd look at the use of phosphite briefly in today's talk. What happens when phosphite is applied to turfgrass? Does it act as a nutrient or a biostimulant? As I said earlier on, it can provide a source of phosphorus, but looking at other studies in other plant systems, there's many reports of beneficial effects from applying phosphite in the areas of growth and quality. And in our field trials, of course, we saw there was an improvement in turfgrass quality. So we said we'd have a quick look and see, try to figure out what was going on when using phosphite in that way. So briefly what we looked at, we had two turfgrass species, Poa annua and Lolium perenne, and we grew them in two different root zones. One was sufficient in phosphorus, had enough phosphorus for maintain healthy growth, but the other one was deficient, around 5 to 6 ppm of phosphorus. So the idea, of course, was to see that did phosphite have any effect on these plants to provide phosphorus that could be used. So we had 3 treatments applied to these plants. One was phosphate, a normal KH2PO4, a normal phosphate fertilizer. The other one was similar, I said it was phosphite. And then as a control, we just used the potassium, as both the compounds actually had potassium in them. So there were the 3 treatments applied, and we looked at the effect on shoot growth, on the crowns and on the roots. And interestingly, this is what we expected in the plants growing in the deficient root zones. Just get my marker out here. These are the 2 turfgrass species. Now this is the leaf growth here. As you can see, the red is the growth of the plants which received phosphate, and they grew pretty well once they received the phosphate. The interesting points here, of course, is to compare the untreated plants, the blue, to the phosphite-treated plants. And you can see in a deficient root zone, when you apply phosphite, it actually has an adverse effect on the growth. And what's happening is the plant is taking in the phosphite and it's recognizing it as a form of phosphorus. And so it's not responding with responses to deficiencies. In the deficient plants, they will enhance their root architecture to extract more phosphorus from the soil and carry out other responses. So this wasn't happening when you were applying phosphate. You can see the untreated controls here actually grew better than the phosphate treated. And this has been seen in other plant systems as well. So the take-home message here would be that if you're applying phosphate to your turfgrass systems, ensure it's in a balanced nutritional program and it's not deficient in phosphorus. Now that was expected by us because we've seen it happen in other systems before. But the next slide is showing the effects of phosphate in a sufficiently fertilized root zone. And surprisingly, what we found here was when applying phosphate, both leaf, crown and roots in both turfgrass species actually grew better than the phosphate-treated plants. There's an enhancement of growth following phosphate. We're not really sure how this occurred. It could be that the phosphate is enhancing the movement of other nutrients through the plant. As I say, we didn't have the time to study further. As we went through our research program, in fact, as we answered a question, there's probably 3 or 4 or 5 or 6 questions that came up which could be followed on. So as with all research, there's actually no end to it. So that was an interesting study there showing the effects of phosphate in a balanced program. Again, just a visualization of the effects on growth here. This middle one is the typical phosphate-treated plant, and you can see the untreated, the just potassium-treated plants here, and you can see here how poor the phosphate-treated plants are. So, like I said, the take-home message from this section would be in a P-deficient root zone, foliar-applied phosphate does not supply a usable form of phosphorus and in fact represses deficiency responses. Whereas in a sufficient P root zone, foliar-applied phosphate actually increased the biomass in all plants, but not shown in the chart. There was actually a reduction in root-to-shoot ratios, but there was an increase in growth from the phosphate treatment. So we're nearly ready to wrap up now, and hopefully you weren't too disappointed or bored with the talk so far. So the overall conclusion of the studies was that the field trials with phosphate showed that there was a significant reduction in Microdocium nivale infection, and phosphate actually enhanced the efficacy of the turfgrass fungicides we used, and a significant improvement in turfgrass visual quality also. The in vitro laboratory studies showed that phosphate suppressed nivale growth. Now we did other studies which weren't shown here today, which showed that it actually just reduced the growth and that it didn't actually kill the fungus. But the phosphate in the growth media actually also disrupted the morphology and inhibited the conidial germination. Our study into the infection process showed that hyphae of Microdocium are the main source of infection, and that it enters the plant via stomata, and that conidia are the means of propagation and dispersal. The defense studies showed that, yes, total phenolic compounds and hydrogen peroxide are key components of defenses. And phosphate treatment enhance these responses, certainly in regard to phenolic compound production. Our HPIC studies showed that when you're applying phosphate to the leaf, it's rapidly taken up and translocates right through the plant. And as I said just a minute ago, in P-limited root zones, deficiency responses are repressed by phosphate, but in a sufficient root zone, phosphate actually increased the growth in the treated plants. So all I can say is that, I would actually recommend phosphate as a valuable addition to any nutrient program. It will reduce disease by at least 50% and allow you to reduce your chemical inputs of fungicides at the same time as improving the turfgrass quality. So we're coming to the end now, and I'll leave you with a photo of the first hole on the Royal Curragh Golf Course, which I look out on every day. And I have to say thank you very much to all of you for listening. And any more questions now? And I hope that I can answer them for you.
Okay, so thank you very much, John. Right now we don't have any question. Well, we'll give some time. Well, let me tell the audience that the files from your presentation are in the session, so they can, the people can download these files. Are in English and in Spanish, so people can choose the language they can download the file. So for me, well, nobody. Well, sorry, there is a question. There is a question from Hector Forten. This guy is a superintendent from Switzerland. He's Spanish, but he's working in Switzerland. And he's asking how many the rates of phosphorus per year and per hectare are you applying to your greens?
The rates of phosphite or phosphorus?
Well, I think that he's asking for phosphorus, but I think he writes phosphor, but well, I think that he means phosphite.
Yeah, well, I apply phosphite to my greens right through the year, every 3 to 4 weeks. As I say, from September through to March, it's very effective at reducing microdopium, which is our major problem. But for the rest of the year, it helps to improve our quality. And it will have an effect, of course, on, we have anthracnose pressure from, say, July, August, and parts of September. So it will help to reduce that. Now, it's not shown in today's talk, but the downside maybe to phosphate, continuous phosphate application, could be increased levels of phosphorus in the soil. So if you're in an area where this is a problem, or it could be a problem, you have to be aware of that. As you say, when phosphate gets into the soil, there are soil organisms which will take up and convert it to phosphorus. So that's something to be aware of. But anyway, I go every 3 to 4 weeks, and it's at a rate of about 0.35 grams per square meter of PO3. So, you know, if you have different products, one product maybe contains 14% phosphite, another product could contain maybe 28, 30%. So, you know, you have to work it out from that. You obviously maybe 10 litres per hectare of the high content phosphorus product, and maybe 20 of the lower one. So it's like any foliar nutrient. You have to work out how much of the actual element is in the product, and then work out how much you want to apply to your greens. But we found 0.35 grams per square meter is a pretty optimal rate.
Okay, he was asking about it because he says he has a lot of phosphorus in the soil. Another question is which is the best way to which are the best forms to apply the phosphites in the course?
Which are the best what?
Best form.
Well, as a liquid.
Which product the best way to apply?
Just as a foliar spray with your sprayer.
Yeah.
Not as a granular. I've never seen any granular forms, but
I think that he's asking for the chemical form.
The chemical form.
Phosphate of potassium.
Well, I think the potassium phosphate would be the best form. Now you can get get aluminum phosphates or ammonium phosphates, but I haven't done it, but I have seen research showing that phosphate in the presence of potassium is actually taken in more rapidly into the fungus. So potassium phosphate would probably be the better form.
Okay. Another question from Antonio Miranda. He's a superintendent from Portugal. He's asking if the phosphates have effect on seed head production on POA.
On seed?
On seed head production?
Oh, right. No, well, I haven't seen that. I wish it did. No, I wouldn't think so. No. It would be great if it was, because we have a lot of problems, through May, June with seed head production. No,
Okay.
I've never seen any work on that.
Okay, perfect. So no more questions. Well, that's all for me. Thank you very much again, John.
No problem.
I think it has been a very interesting presentation, because we are in an increasing restriction on chemicals here in Spain and in the most part of Europe. So
yes.
we have to look for alternative tools to manage the turf.
Of course, yes.
Sorry, now there are more questions. Let me ask you. Yes, there is a guy. He's asking if you have evaluated the use of phosphatyl aluminum against microdocum nivale.
No, I haven't used that. I haven't actually got it here in Ireland. I'm sure it would be. I'm sure it would be effective, all right. But I haven't used it, so I couldn't say.
Okay.
It's very effective, of course, at controlling pythium. Again, we don't get pythium in Ireland.
Oh, you're lucky.
We don't have the weather.
Okay. Another question. Do the phosphites affect negatively to the microbes?
To the what? Oh, microbes.
Yeah.
Not that I know of. I mean, quite a lot of them actually take up phosphite and use it, and the byproduct is actually phosphate. But again, I haven't studied fully that, so I couldn't say for definite. But like I said during the talk, there's a huge amount of questions that came up during the study, which you could follow on. I mean, one that I often thought of was the effects on mycorrhizal fungi, whether phosphite affects that, for example. But that's one. Again, the effect on soil microbes would be an area that could be followed up. A huge amount of questions still to be answered.
Okay. Another question. Apart of microdocum nivale, do you think that may phosphites affect or reduce another pathogens?
Sorry, what's that?
Do you think that phosphites may affect to another pathogens?
Oh yes, I'm sure they would. We've seen that they affect Colletotricum, the anthracnose pathogen. So, and I've seen it in other non-turfgrass pathogens as well. So again, it's down to the competition between phosphite and phosphate. All pathogens or all fungi need phosphorus to grow. So once phosphite is interfering with the uptake of phosphate, it's going to have an effect on the fungus.
Okay. Another one. Do you still have time?
Yeah, I have plenty of time.
Yeah. Okay. Have you ever tried applying mycorrhizas with phosphites?
Have I tried mycorrhizal fungi?
Yes, with phosphites.
No, I just like I said a minute ago, it's an area of that could be studied. Now there was a study done, I think it was 2001 in Australia, looking at the effects of phosphite on mycorrhizal fungi, and they didn't find any great effect on it. But I would think, if once phosphite is in the plant and has been taken in by the mycorrhizal, it would have an effect on it. But I couldn't say. I haven't studied that.
Okay. Francisco Piñeiro is asking, if you can recommend any commercial brand on Spanish or on an Irish market.
Well, I don't really like to recommend commercial products now, to be honest with you.
Yeah.
But mostly because unless I actually have tried all the commercial products, I couldn't say which one is the better one. Now, I do use one myself on the golf greens, which is the American product from Griggs Brothers. But that's the one I use. But I couldn't say, that it's better than some other product, unless I actually directly compared them. It's like all fertilizers which are available. Everyone has their own preference. Uh, Really, once they're made correctly, they should be all effective. So some are different, of course.
Okay. Difficult to answer this one.
Yeah, yeah.
Yeah, no, I understand.
I'm not here to. I'm not here to promote,
Yes,
products.
yes, of course. Okay, so no more answers. No more questions. So, well, that's all. Thank you very much again for your interest, for your collaboration, and well, maybe we can do another presentation in the near future if you agree and if you want.
Okay, perfect. It's a bit odd. I'm sitting here at home in my office with just the dog here. So,
Okay, thank you very much. Right now I'm gonna speak in Spanish to say goodbye to the attendees. So, por mí,
okay.
bueno, okay. Bueno, pues nada, pues nos despedimos de vosotros. Solo recordaros que tenemos programado. Dejadme que os prepare Vale, a ver. Tenemos programado para el día 10 de noviembre otro webinar que contaremos con la presencia, con la presentación del profesor Fred Yelverton. Pues tratará sobre la gestión de malas hierbas en campos de golf. Espero que os podáis apuntar. Será también otro webinar muy interesante. Y nada, como siempre, contando con la colaboración de nuestros socios, como son Compo Expert y Syngenta, Semillas Fito y Jacobsen. Gracias a ellos y a la colaboración también con la Asociación Española de Greenkeepers, pues vamos ofreciendo estas sesiones formativas. Y nada, pues muchas gracias a todos y espero veros en el próximo webinar.